This chapter provides an introduction to the real-time clocks available for the Msp430 family of microcontrollers. What is a real-time clock? It's just that. It's a timer that provides clock and calendaring features. Beyond that, most real-time clocks also support alarms. Most of us probably understand the concept of alarms because we often wake to them each morning. Bottom line though, these alarms are really just CPU interrupts. One last important feature is that the real-time clock peripheral has been designed for very low power. It is common to let the RTC run while the processor sleeps. An alarm interrupt then can wake up the CPU to perform some task at a specified time or interval. Let's begin by looking at how the RTC works. The RTC peripheral is usually driven from a 32 kHz clock. In the case of the RTC A variation, you can choose either A clock or SM clock. The A variation is found on the F5529 and provides this choice so that you can drive it from the external crystal or the internal reference oscillator. On the other hand, RTC B, which happens to be found on the FR5969, is driven directly from an external low-frequency crystal. This CPU doesn't have an internal 32 kHz reference oscillator, so an input source option isn't required. But one of the advantages of being driven directly from a crystal means that this RTC can work in LPM 3.5 mode. As shown here, the clock input is divided down by two prescale counters. These take the clock input down to a 1-second resolution. From there, the registers in the RTC can keep track of minutes, hours, days of the week, day, month, and even the year. You can use these values to create timestamps, set time, calendar displays, for example, like on a watch, and so on. Okay, but what about alarms? That is, what interrupts can the RTC generate? There are 6 types of RTC interrupts. 1. You can generate an interrupt whenever the value in the time register matches its associated alarm register. 2. An interrupt can be generated when RTC count events occur. This can happen at each minute, at each hour, or whenever the time reaches midnight or noon. The RTC also has the flexibility to generate additional time-based interrupts from the prescale counters. For example, whenever a prescale counter is divided by 2, 4, 8, 16, 32, 128, or 256, an interrupt can be generated. Because we have 2 prescale counters, that gives us 2 more interrupts, what we call interrupts 3 and 4 in our list of 6. As we'll note in a later slide, you need to exercise caution so that you don't read the RTC registers while they're being updated. To make this easier for you, the 5th type of RTC interrupt indicates when the RTC registers are ready to be read or written to. Finally, the 6th type of interrupt is for an oscillator fault. On devices that allow the RTC to run in LPM 3.5 mode, the CPU would not be able to directly detect that an oscillator fault occurred. Therefore, this RTC interrupt can wake the CPU if something's gone wrong with the external clock. Now that we have all of the interrupts shown on the slide, notice that each of the 6 interrupt types have their own associated interrupt flag bit, or IFG bit. As you might suspect, they work similar to the other IFG bits that we discussed back in the interrupts chapter. In this chapter, we briefly examine 2 different ways to program the RTC. While we don't currently use the Grace graphical development tool to program the Msp430 in the workshop labs for this course, programming the RTC exemplifies just how intuitive Grace is. Fill in a few blanks and check any interrupts you want to enable, and voila, Grace will write the driver library code for you. The other solution we'll examine is looking directly at the driver library code, which is shown on the next slide. Writing the driver library code is straightforward, although not quite as cool as looking at the Grace GUI. Once you've configured the calendar, alarms, and events, as we've done at the top of this slide, you just need to clear and enable the interrupts you want before starting the RTC. After all that, this example just enters LPM 3, although that isn't necessarily required. Before we finish the chapter, Let's just look at a few additional considerations. As we show here, all RTCs can operate in the low power mode 3. Since RTC-B and RTC-C can directly access the low frequency crystal, they can also operate at the LPM 3.5 mode. This is great because it provides the lowest power timer calendar feature. RTCs B and C also provide convenient hardware conversions between BCD, that is, binary coded decimal, and hex, if you should need it. On the other hand, RTC-A contains a 32-bit counter mode that isn't present on the other RTCs. Finally, we wanted to caution you on a few issues. 1. The user's guide highly recommends clearing bit fields before you set them. 2. Invalid time and alarm settings are not trapped by hardware. If you make a mistake, you will get erroneous results. 3. You should not read or write to any RTC register when the peripheral is updating them. Again, you'll get erroneous results if you do so. To keep this from happening, the RTC provides a ready bit that lets you know when it's okay to read or write its registers. You can poll the ready bit, or better yet, use it to interrupt the CPU when the registers are available. In fact, this is one of those interrupts we talked about earlier. Finally, you could just hold the RTC before accessing its registers, but the method we prefer most is using the ready bit as an interrupt. To summarize, this summary table shows the differences between the 3 RTC variations found across the Msp430 family. The F5529 happens to use RTC-A, while the FR5969 uses the RTC-B peripheral. The G2553, which we've often discussed in this course, doesn't contain an RTC. That concludes the chapter on real-time clocks. Currently, we don't have a lab exercise for this peripheral. We suggest that you refer to the examples provided by the Msp430ware driver library team.